If all is well, you guys can now see the screen. So
yeah, it's visible.
Very good. I'm not with you. I'm far away, but still I'm happy to be here and tell you, give you an introduction basically on quantum computers. I have no idea really whether this will be too simple or too difficult. I've tried to somehow have something for everyone. And by all means, if you want to ask questions while I'm talking, just raise your hand in this Teams window, and the chair, our friend who is chairing this, will give you the floor.
It's hard to pronounce.
Yeah, very good. So this is about quantum computers, which is somehow a new technology, and it's not yet fully advanced, but at some moment it will become advanced. And then what it does is actually, it seems like magical. And there's actually Clark was a science fiction author who made this observation that if you look at technology and you don't really understand the ins and outs of it, it looks like magic. Think about, airplanes which fly in the sky and speaking over long distance. Actually, the fact that I'm able to speak to you here, just sitting behind my desk here in the Netherlands. If you have no idea how this comes about, it's a magic apparatus. And quantum computers has some of that magic, in particular because it's quantum, and the quantum world is not a world which we're very familiar with, even though we may get courses in quantum physics when we study physics. In my country, even high school students get some exposure to quantum physics, but it's still a completely magical world. Now, I will be talking to you about computers. So let's just step back a little bit and think about classical computers, the usual type. And if you're a fundamental person, you might say that the way we calculate hasn't really changed in thousands of years. So this object here is an abacus. It's a counting device. I guess that's how people counted or kept track of numbers 1,000 years ago, or perhaps even longer ago. It's a digital device, I think. I'm not even sure, but it's base 10 or base 12 or base 16. I don't know what people used in those days. And we know that computers calculate in base 2, so they're either 0 or 1. But if you're a fundamental person, you'll say that it's a detail. The fact whether it's digital, base 2 or base 10 is irrelevant. We still have numbers, we add them, we subtract them, we multiply them. And from that perspective, a classical computer is just faster and makes less errors, but it's equivalent to counting on your hands. That is the first observation which I would like to make. And the story which I will be telling you today is that a quantum computer, for the first time in the history of mankind, is about doing calculations in a fundamentally different way. So a classical computer is not fundamentally different from an abacus, but a quantum computer is fundamentally different, and that's the exciting new development. Now this is another slide which shows the inside of a classical computer. It shows a chip, all kinds of transistors.
I think we can see the slide. Like, you didn't change anything.
You should see slide number 3 now, which says classical computer.
It's just slide 1 for now.
Oh my goodness.
Oh.
You don't see me changing slides?
No, not at all.
Not really. It's just slide 1, quantum computers.
Okay, that's not good because I'm already at slide 3. I have no idea. Let me see. I don't know. I typically give talks using Zoom. I've never given talks using Teams. I don't know.
So
I'll stop the share.
Sharing screen, did you share your screen?
I'll share the whole screen. Now I'm sharing the whole screen.
Yeah, it's better. It will probably change slides now.
Let me see if I change it now. Now you see me changing the slides?
Yeah, we do.
Yes, we can.
Okay. Good that you warned me, because this would have been really embarrassing if we continue for the whole talk without changing slides. So I showed you the abacus, right? I was talking about the abacus. You didn't see the abacus. Here it is. This is the abacus. And you didn't miss much. So that's the classical computer. There's the other thing about classical computers, which is that the operations on the classical computer are irreversible. That's really important. And for example, if you think about a classical computer becomes hot, right? The computer which you have on your laptop becomes hot, and hot is a signature of dissipation. It's a signature of irreversibility, if you wish. And that's really important. And I show you here a logical gate. This thing here is a logical gate. It shows, I think it's an OR gate. It shows 1 and 0 as input, and the output is 1. So it's an OR gate, and the OR gate is irreversible, of course, right? If the output is 0, you don't know whether the input was 1 0 or 0 1 or 1 1. So gates in a classical computer are irreversible, and that's important actually because it gives the computer a certain robustness. Think of, for example, a light switch which you may have in your office, right? You toggle the light switch from on to off. And there's some spring inside, I imagine, but it stays put. It's not that it's going to oscillate up and down. If there will be no friction, the moment you give the on-off switch, you push it, it would just start toggling up and down. But there's friction which blocks it into the on or the off state. So dissipation in a classical computer is very important. It gives you stability. It also gives you heat, which is awkward, and you want to get rid of it. But it's important because it gives you stability. Now let's go to the quantum computer. So the first thing about the quantum computer is that it's not binary. It doesn't use binary logic. It's basically an analog device, if you wish. It does have zeros and ones. But the fact that it's analog is because you can interpolate between 0 and 1. And I've written an equation here which somehow should show that. It shows a 0 and it shows a 1, and there's a weight factor. This weight factor is alpha. It's square root of alpha. That's the magic of quantum, that it has to be square root. But it doesn't really matter very much at this moment. You could imagine if alpha is 0, then it's fully 1. If alpha is 1, then it's fully 0. So this is something which interpolates between 0 and 1. That's the first thing. It's analog. But it does so in a way which is very counterintuitive. Meaning, even if it's interpolated between 0 and 1, so suppose I'm halfway between 0 and 1, it's actually 0 and 1 at the same time. Instead of being halfway between 0 and 1, it's 0 and 1 at the same time. That's something which is counterintuitive. And it really exists in a laboratory. I show you a picture here with a superconducting ring. It's a small device, a small ring. And there's a current flowing through the ring. And this current can flow clockwise or counterclockwise through the ring. And you could imagine if it flows clockwise, I call it 0. If it flows counterclockwise, I call it 1. But the crazy thing is that if this ring is in this superposition between 0 and 1, the current is flowing both clockwise and counterclockwise at the same time. That's the magic of quantum. It's said that quantum doesn't choose between things. In the quantum world, we don't choose. We have contrary things coexist at the same time. Now, if you follow the course in quantum physics, you know that we have developed a certain notation to explain this counterintuitive behavior. I showed you the notation here on this slide. There is a 0 and there's a 1, and there's this little bracket which protects the 0 and the 1 and prevents you from actually adding them. You're not supposed to really add them. They're not numbers which you can add. They're things which exist at the same time. And so this is somehow a notation. It's math, and that's basically what we have because it's counterintuitive. We don't really know what's going on. We use mathematics to somehow make sense of it. And those of you who have been exposed to quantum physics will have learned how to work with this math. Now, in the superconducting ring, so it's the current which flows clockwise or counterclockwise, but there are other possibilities. You can have electrons which have a spin, which can point upwards or downwards. That could be the 0 or the 1. You can think about light, a photon, the particle of light, which can have a polarization, which could be circularly polarized left or circularly polarized right. There's ions. So there's a whole bunch of systems which can make what's called this qubit. That's the word we use for this. It's a bit which is quantum mechanical, and so we call it a qubit. It's in a superposition of 0 and 1. That's the first anomaly. The second anomaly is that this quantum world does not tolerate dissipation. Every operation which you perform on a qubit has to be reversible. There can be no dissipation. If there's dissipation, you just reduce and fall down into the classical world. So that's not very helpful, but it's something we just have to live with. And so this OR gate, which I showed you a slide before, which is an irreversible gate, is not allowed in a quantum computer. In a quantum computer, we only have reversible gates. Here is one example of a reversible gate. It's called the controlled NOT gate, which means C0, controlled NOT. It's like this. You basically have the 0, that's at the bottom, and the 0 switches to a 1 only if the other qubit is in state 1. So if the other qubit is in state 0, you don't do anything. If the other qubit is in state 1, then you flip the 0. So NOT means flipping from 0 to 1. And it's controlled by the first qubit. And this notation here is how we denote the C0 gate in the diagram. So it's reversible because I can always go back if I know what's at if I know what's at the right end, I can always read the diagram from right to left. So it's a reversible gate. So these are the differences between classical and quantum computers. And now you might say, okay, this is all, let's say, elementary quantum physics. How can you do anything useful with this? And as you know, we're now in the year 2025, which is the centennial of quantum. I'm not sure whether this is celebrated in Turkey. In my country, it's certainly celebrated. The year of quantum, we call it. There are lots of festivities because 1925 was, let's say, the first most important quantum publications appeared in 1925. So this idea that you could use quantum to do calculations is relatively recent. It's not something from the early 20th century. It's from the late 20th century. If you go back, you can even go back as far as 1982, which is really going back very far. But there's scientists Richard Feynman, Paul Benioff. They imagined that you could use quantum logic to calculate things which you could not do in a classical computer. They were basically thinking about problems in physics, simulation of physical processes, superconductivity, magnetism, all kinds of material science calculations, perhaps even quantum chemistry calculations, all kinds of molecular calculations which we find it very difficult to do in a classical computer. And their reasoning was like this. They say, why is it so difficult to calculate a large molecule on a computer? It's because a large molecule follows the laws of quantum mechanics and our computer follows the laws of classical mechanics. And so we don't understand each other's language. And so what you should do is you should have a computer which speaks quantum mechanics, and then it will have no problem in figuring out what this molecule will do. And this machine which speaks quantum mechanics is what you could call a quantum computer. So that's the first. The second prehistory paper is a paper from the 1980s, also David Deutsch, who I guess is waiting to win the Nobel Prize for having discovered quantum computing. He tried to make sense of this idea that qubits could be both 0 and 1 at the same time. And the way he tried to make sense of this is that it actually there are different universes. There's one universe in which the qubit is 0. There's another universe in which the qubit is 1. Think about this ring. I had this ring with the currents flowing clockwise or counterclockwise. I could imagine that there's one universe in which it flows clockwise, another universe in which it flows counterclockwise, and that's why we cannot decide which of the two it is. And if you somehow carry this logic further, you'll say, if you have a whole bunch of qubits, each calculating in a different universe, it is as if you have a sort of a massively parallel computer. Massively parallel because if you think, suppose you have like 10 qubits, right? You might say, how many different possibilities are there? If I have one qubit, there are just 2 possibilities, right? If you have 10 qubits, it's 2 times 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 2. That's 2 to the power 10 possibilities, which is a huge number. If you have 100 qubits, it's 2 to the power 100. That's such a large number, you wouldn't be able to write it down. That's why it was called massive quantum parallelism. And we know that, of course, even classical computers work in parallel. Any computer you have these days will have a bunch of processors, perhaps 6 processors, perhaps 8 processors. So parallelism exists also in the classical world, but it's very expensive, right? You have 8 processors, you have 9 processors, you have 10 processors. With qubits, every qubit you add doubles the number of processors, if you wish. So this is a sort of massive parallelism, which in the eyes of David Deutsch was an untapped resource. So that's the prehistory. Now, let's see how this parallelism might work. And I will try and flash a few simple equations. If you've seen this before, that's good. If you haven't seen it before, perhaps you can still extract the flavor of it. So here on the top line, there is the 0 plus 1. That is a qubit which is in a superposition of 0 and 1. So it's both 0 and 1. Now forget the square root of 1/2. That's some sort of that's this parameter alpha which I showed you before. We're not going to keep track of that. Now if I have n qubits, so this was just 1 qubit. Now if I have n qubits, then the n becomes 0 plus 1 to the power n. So it's 1 qubit which is 0 plus 1, the other qubit which is 0 plus 1, and I have a whole bunch of them. Now imagine working out this product like you learned at high school, right? 1a plus b squared is a squared plus b squared plus 2ab, right? Remember? So imagine working out this product. Then you get a string of zeros and ones. And the string of zeros and ones is actually a binary number. Right? So here I wrote down one example of such a string, 101001101. It's a string of digits. It's a binary number. And if you actually work out this 0 plus 1 to the power n, you'll find that you get a sum of all binary numbers between 0 and 2 to the power n, 2 to the power n minus 1. Now, how many operations did you do? Basically, you did one operation on n qubits. You could imagine that this qubit is the spin of an electron, which is pointing upwards. And then 0 plus 1 means that you rotate it by 90 degrees. So it could be a magnetic field pulse, something like that. So you've done one operation on n qubits, and you end up with 2 to the n digits. Imagine having to write down 2 to the n digits. It's going to take you days. If n is 100, it would take you a lifetime. But here you've done it with one operation. So that is this massive parallelism. You've generated exponentially many numbers in one step. Okay, that's the first ingredient. Now comes the next ingredient, and that's actually the typical nonsense which you see in popular talks about a quantum computer. Now, this is a popular talk, but I'll try not to make this mistake. And the nonsense will be that one quantum computer with n qubits is as powerful as 2 to the n classical computers. That's a typical phrase which you may even find in Wikipedia, perhaps, but you certainly will find it on the web. And this is, of course, it goes back to this particular equation here. You say you've generated 2 to the n numbers, but the problem is these 2 to the n numbers are just hidden in these qubits. If you would do a measurement to say, okay, let's read out these numbers, you get only one value of x. Right? So if even though the left-hand side of this equation has these 2 to the n numbers, the moment you do a measurement, you get only one value. And to get all the 2 to the n values, you would have to do 2 to the n measurements, and then we're back to something which will take forever. So even though as a notation, it seems as if you've generated 2 to the n numbers with one operation, in practice, it's not really like that. It's more a question of notation. There's some... It's a confusing thing. It's not like that. And in fact, this is actually one of the problems we have with quantum computers, that it's not obvious what you can do with them. If a quantum computer would indeed be as powerful as 2 to the n classical computers, you would be in business. You'd say anything we feed to our computers, anything, we just feed it to a quantum computer and it will speed up our life. But it's not like that. In most cases, you won't get any speed up at all. No speed up at all. In fact, we do not really know at this moment how to get a useful speed up. There's one or two examples. Let me show you one particular example. This is actually the first example, and it's the one which basically started the whole field. It's 1994, when Peter Shor, a computer scientist from the United States, discovered that actually a quantum computer can break codes. So this is one very special application. So as you know, a code is the thing we're using on the internet when we transmit our password or a credit card number. We'll have a secure communication line. It will say HTTPS, right? It will be a secure line. This means that our information is encrypted. And the code which encrypts our information is designed in such a way that it's very difficult to break it. People will tell you, okay, if you have a computer, you could try to break my code, and it would take you 1,000 years. And what Peter Shor discovered is that actually the typical code which we use at this moment, which is called RSA, that this particular code could be broken in a quantum computer in a matter of minutes, if the quantum computer was large enough, if it's large enough. So this, of course, and the language in which this is phrased in computer science is that they say that the time to break a code with a certain number of digits, instead of being exponential in the number of digits, it's only a power law in the number of digits. So exponents grow absurdly rapid. I see a hand there.
Yeah, I was about to.
Please go ahead.
Yeah, thank you. But doesn't it mean that we can also generate a code that's generated by a quantum computer that is also unbreakable for even another quantum computer?
Yes. So this is so. Let me continue this line of thought in just a moment. I'm going to answer your question, right? So when this was 1994, right? So this was like a nightmare for all kinds of people who have real secrets, right? Human beings like me and probably you do not really have secrets, but just embarrassing things. But if you're a banker or if you're a general, and then secrecy is very, very important. So when this was found, this created a big shock. And there are basically two ways to counter the shock. Two ways. One way is to say, okay, that's RSA, which is a certain code, which is broken by a quantum computer. We're just going to invent another code. RSA is just one code. We'll just invent another code, simply because a quantum computer is not a universal computer. If we invent another code, perhaps someone like Peter Shor will again find out how to break it, but just as likely he will not find out how to break it. So that's one route which people are following. And these other codes come under names of, for example, elliptic codes. And in fact, there's now some sort of standard, I think it's mainly in the United States, which gives out codes, which says that if you want a quantum proof code, a code which is presumably safe for quantum computers, use one of these elliptic codes. They tend to be more expensive in the sense that they're slower, they need more computer power, so they haven't yet migrated to the internet, but they will. There's even a word for this. The word for these codes is called post-quantum codes. So post-quantum meaning after quantum. They're just classical codes, no quantum computer. They don't need a quantum computer. They're classical codes, but they're somehow different from RSA, and Peter Shor hasn't invented the way to break them, and perhaps nobody will find a way to break them. That's one road. It's the most natural way to do it, and I'm pretty sure within a couple of years you'll find that lots and lots of people are using these codes. The other way to do it, and that was what your question was alluding to, perhaps you could use a quantum computer to make an unbreakable code. This is also possible. It's called quantum key distribution. The problem, of course, with that is that you would first need a quantum computer to work with it. And most of us don't have a quantum computer. And they're small, and so quantum key distribution, which is actually the basis of what's called the quantum internet. The quantum internet is something which presumably at some point will take over from the usual internet, and it will use quantum computers to transmit information. This is distant future, if at all. If at all it happens, it's distant future. The furthest in the quantum internet is China. China has a satellite which does quantum key distribution. In Europe, they're trying to make small nodes. In my country, there are nodes between a couple of cities. Perhaps there's even a small quantum internet in Turkey. I don't know. It's a relatively easy thing. It's not a very complicated thing to have a few cities connected by quantum internet, but it's absolutely no stage to be used at this moment. Whereas these post-quantum codes, they're stuff which you can just implement. Probably you can download one today and make sure that your communications are quantum safe. So that was the first breakthrough. That was 1994. I have a slide here which somehow explains how it works. I'm not sure if I'll tell you. I'll just spend 1 or 2 minutes to show you this slide. It's one of the more technical slides. So I'm not a number theorist, but if you're a number theorist, you know that the reason why RSA works is because it's very difficult to find prime factors of very large numbers. If you give you some number with, I don't know, 1,000 digits, and I tell you this has 2 prime factors, you will never find them. And that's the way these codes work. And behind this, so there are many algorithms actually to find prime factors, and they all boil down to finding periods of a function. So I give you a function, I tell you the function is periodic, and I ask you, please find the period. It could be a binary function, but it's periodic. And if there are many different inputs, before you found the period, you may have to perhaps even try as many as half of the inputs, because you just have to be lucky. And in quantum physics, you can just do it with a very small number of operations, and this is basically how it works. So there is a function f of x which has an unknown period a. I take two qubits, 2 rows of qubits. In one row of qubit, I store this number x. In the other row of qubits, I store the number of f of x. This goes back to what I showed you on the previous slide, right, where I showed you how to generate exponentially many numbers. So here I have exponentially many values of x and exponentially many values of f of x. And then I measure the second row. I measure the second row. I have no idea what comes out of it. Some number fx0 will come out of it. And then magically, and this is the magic is that magically the first row will have all the x's, which will give you this f of x0. So it will have x0 and x0 plus a, x0 plus 2a. And you're done. This is the magic of quantum physics. How with one operation, you basically find this hidden periods. You would need 2 to the n or 1/2 times 2 to the n operations if you would have to do it classically. There's a question there. Please go ahead.
Wouldn't this be a threat to our encryption models?
Yes, this is the operation which breaks RSA.
All right.
This is why a quantum computer can break RSA and break all variations of RSA which rely on the difficulty of factoring large numbers. Of course, it's not. There are other ways to encode information which do not rely on this thing, but all the typical ways to do this, which rely on the difficulty to factor large numbers, they're all broken by quantum computers in this way. So this was a shock, because before all this business was just, some academic stuff, some people playing, writing papers. Nothing seemed particularly serious. When Peter Shor came with his paper, everybody took note and said, "Oh my goodness, this is important. We have to, people in boardrooms, the military." People said, this is, imagine that the Chinese find out, imagine that, I don't know, Russia finds out. So there was all this excitement. This was the 1990s. The excitement in the 1990s was basically the quantum computers are a danger. They're a danger for our intelligence. Now, what has changed now, we're 20 years later now. First of all, we've realized that this is not such a big deal. We'll just find other codes. And we've realized that actually this is a very boring application of a quantum computer. It's a boring application to break a code. Who cares? You want to do good stuff with quantum computers. You want to, do useful stuff with it, good stuff, make money with them, make money with quantum computers, not break codes. And that's something which we have now learned. I will come back to that in just a moment. But first, I want to just mention one other breakthrough. So I mentioned the breakthrough from 1994. That was Peter Shor. And then there was another objection. This was Rolf Landauer from IBM. He said any operation in computing, in computer science needs error correction. The computers are not perfect, there are errors, and we correct for them all the time. Everything we do on a computer, on the internet, it's all continuously corrected. That's what gives it robustness. Now, the problem with qubits is this. If you measure a qubit, you destroy it. If you measure it, you destroy it. So how can you correct errors if you're not allowed to look at the qubit? The qubit is this black box. You're allowed to look at it only at the very end of the calculation. Then the answer drops out. So you have these qubits, they do their thing. At the very end, the answer falls out, but you're not allowed to open the box and look what's going on. And so Landauer said, okay, so if the box is closed, you cannot correct it, and it's fundamentally impossible to make any computer which cannot correct errors. And then in 1996, Steen and Shor, again Shor, they found how to do quantum error correction, meaning how to correct errors without reading out the qubit. Again, it's something, if I tell you, say it's impossible. If I'm not allowed to look whether you've made an error, I cannot correct it. I cannot help you. You go to the teacher with the exam and say, I think I've made an error. And the teacher says, please, can I look at your exam? I don't want to show you my exam. And the teacher says, I can't help you. But in quantum physics, it's possible. Here's how it's done. There's another question here. Please go ahead.
Is it like Schrödinger's cat?
Yeah, well, Schrödinger's cat is what tells you that you cannot look at the cat, right? The cat is in a superposition. I mean, Schrödinger's cat is just a dramatic thing about the qubit being in 0 and 1. If you look at the cat, then it's either 0 or dead. And if you don't look, it's both 0 and dead. But that's just it's a joke, so to say. Here we have a qubit. It's 0 and 1 at the same time. But the moment you look, it's gone. It's either 0 or 1. So you're not allowed to look at the qubit. And here's how it's done. You take a qubit and you just, you repeat it. So instead of saying 0, I say 0, 0, 0. Instead of saying 1, I say 1, 1, 1. So I have my original, which is, let's say, 0, 0, 0 plus 1, 1, 1, instead of 0 plus 1. And now one bit is flipped. I don't know which one is flipped. I'm not allowed to look. I'm not allowed to look whether one is flipped. One is flipped. Perhaps none is flipped, but if one is flipped, then one is flipped. Which isn't? Here's what I do. I just do a parity check. The parity check is a simple circuit. Here you see it's just a bunch of CNOT gates. A bunch of CNOT gates. A parity check compares which two qubits are different without measuring them, without telling you whether they're 0 and 1. It just says, are they the same or are they different? And of course, if you do that, then you will know which spin is flipped. You first compare the parity of the first two, then you compare the parity of the second two, and then in this way you'll be able to find out whether you also the parity of the last two. In this way you'll find out which one differs, and the one which differs has flipped. So you flip it back without reading off. So without looking whether I'm going to flip a 1 into a 0 or a 0 into a 1. No, you're not allowed to know. You just know, I don't know what it is, but whatever it is, it's wrong. So whatever it is, I close my eyes, I don't open the blocks, I just apply my magnetic field and I flip it without opening the box. And that's brilliant and it works. And this has now become a huge industry. It's called quantum error correction. It's a big industry. I mean, this is just a baby element of it. It's a huge industry how to do error correction on the quantum computer. So that's good. Now, okay, so I've described to you a little bit the basics. So where are we now? Now it's 2025. Where are we? We've been doing this stuff for 20 or 30 years. And what have we done? Well, first of all, the quantum computer exists. They're prototypes. They're prototypes which you can basically access on the web. Probably some of you have already done that. There's some platforms where you can just log in and use it. IBM has one of these platforms. It's called Quantum Experience. Google has its own platform, which it doesn't open it up to the public. China has a very elaborate platform, which probably is also not open for the public. These are the three players which I think have the most qubits at this moment. They're all use one particular technology, which is the technology I showed you in my very first slide, where I showed you this superconducting ring with the current flowing clockwise and counterclockwise. Superconductor is something, it's actually a Leiden discovery. Leiden is my university discovery, I think 1911, somewhere around that time, that if you cool certain materials very much, then a current can flow without resistance. Now, a current which flows without resistance means a current which does not have dissipation. So that's good. I want that because my quantum computer does not tolerate dissipation. That's why superconductors seem, at least in an initial stage, they seem like an ideal vehicle for a quantum computer because you have currents which will never decay, no dissipation. They have other problems. They have a bunch of problems. So it's very possible if you look back 10 years from now, we'll say, the superconducting qubits, that's how the field started. But they've been completely replaced by something else. One problem, of course, with superconducting qubits is that you have to cool them down to close to the absolute zero, which is not that big a problem, but it's an issue. Here you see some of these fridges. You see these huge fridges, and deep inside are these qubits. And you access them through the cloud. So, for example, if you would log into Quantum Experience, this is what you would see. So this is the IBM Quantum Experience. This slide is, the picture is a little bit old. At this moment, they have 127 qubits. I don't think you can use 127 qubits without paying. Probably they will only allow you to use a couple of dozen qubits without paying. But if you pay, it's like with ChatGPT, right? You get some basic functionality without paying, and then you can go pro. You pay a little bit of money and then you get the full thing. So if you pay a little bit, you probably get the whole 127 qubits. And they have a roadmap. They promise, I think they've promised 1,000 qubits this year. So this is going pretty well. This is how it looks like. So this says Q20, Q16, Q5. This is the number of qubits, 5 qubits in some array, 16 qubits, 20 qubits. And so this is actually the 5 qubit device. Here are the 5 qubits. and this is the frequencies, the clock speed. And then here there's something, a number which may give you pause. It says T1 and T2, and it says microseconds. A microsecond is 1 millionth of a second. This is the time after which it crashes. So this IBM quantum computer crashes after something like 50 microseconds. So any program you run on this computer has to be short, because if it's too long, it crashes. And so there's a big industry here in trying to somehow chop up your big program into short programs so that you can somehow run it crashes, and then you can restart it, and in this way make progress. But obviously this is a big issue. So there are two issues with the current computers, the current quantum computers. They exist, they're okay, you can do stuff with them. The number of qubits is not very large. Still, it's kind of sizable. I mean, it's not 2 or 3, it's a good number. But they crash very rapidly, meaning the qubits are not very good. And so we need to basically improve on both sides. We need to have more qubits. Typically 1,000 qubits, if they would not crash, would be brilliant. I mean, it would all you need. 2 to the number 1,000, 2 to the power of 1,000 is so large, you could solve every conceivable problem. But of course, it should be able to run like a second. The clock speed here is gigahertz, so the computer is fast, but still, you want programs which can run for a couple of seconds, perhaps a couple of minutes. For that, of course, we would need error correction. So you need something which the computer will crash, but if it's only one of the qubits which crashes, probably you can correct it, and so you can somehow move on without too much of a penalty. And these are actually the designs which people are making at this moment. They distinguish between what they call physical qubits and logical qubits. They'll say, you know what? I would be very happy if I would have one single qubit which doesn't crash for a minute. And I do that by encoding the information in 1,000 qubits. Remember I had this slide here where I said encode in 3. This protects from 1 error. Imagine encoding it in 1,000. So saying 0 is actually 0, 0, 0, 0, 0, 0, 0, 0, 0 up to 1,000. Then I can correct, so many errors. So this is the overhead. This is the overhead which quantum computers have at these days. The overhead is that there could be many physical qubits. The number of logical qubits, the number of protected qubits which do not crash is very small. It's very, very little. There was this recent Google breakthrough, the Willow chip. You may have seen it. The Willow chip has 105 qubits, and it has 105 qubits which serve to create one qubit which lives longer. So that's the typical overhead we have at this moment, a factor of 100. That's one thing I want to show you. The other thing I want to show you is say, okay, still it's cool. I'm going to play with this. How do I program this thing? Is there a programming language? Well, there's a bunch of programming languages. And basically, Microsoft has positioned itself as the hub for programming languages. It's called Azure Quantum. They basically want you to, whatever the quantum computer is, they want you to go through their platform, through their portal. But it doesn't really matter. I mean, they all look pretty much the same. So think about an old-fashioned calculator, right? An old-fashioned calculator, one of these pocket calculators, it would have numbers, and then it would have digits. You could press like a plus button, or you could press the times button, or the divide button, or the minus button. And in this way, you could do a little calculation. Now, you might imagine that the quantum computer will also have a plus, or a times, or a minus, or a divide, but it does not. And the reason is what I said to you at the very beginning. All operations on a quantum computer have to be reversible, and the plus operation is not reversible. Even if I restrict myself to digits, if I tell you I've added 2 digits in the numbers 8, you don't know, is it 3 plus 5? Is it 4.4? Is it 6.2? So adding numbers, multiplying numbers is not reversible. And so you cannot implement it natively on a quantum computer. This is actually a disaster. You imagine you have a quantum computer, the most powerful computer on Earth. It cannot add or subtract. It cannot multiply or divide. Well, eventually it can, but you have to go through a big detour to somehow hide this irreversibility of the plus operation. And so there are even jokes on the internet where they take one of these quantum computers and say that, you know, it adds 2 digits to single digit and gives you a 20% error, which is true. It's a very unnatural operation for a quantum computer. It's one of the last things you want to do. So what are the basic building blocks? They're reversible operations. And here you see, so this slide here shows you how a programming of a quantum computer looks like. At the very left side, there are these qubits, right? I have 5 qubits here. They're initialized in the state 0. And then I read the whole thing from left to right. I read it from left to right. And at the very far right, you see this little dial that says, I measure it. And in between, you don't measure anything. You measure stuff at the end. And then you put in these little boxes. Now, you can see some of them you'll recognize. There's this one with the thing with the plus. The thing with the plus here, that's the C0 gate. We've had that before. That's the C0. There's this thing which is kind of trivial, which is called ID. It's the identity. It means don't do anything. Identity just means leave that qubit alone. And then there are other qubits. They're called X, Y, and Z. You see them here. There's an X, there's a Y, there's a Z. X, Y, and Z are simple logical operations. The X is the not operation. The not operation is reversible, right? So that's good. The not operation is reversible. That's the X. The Z is a simple operation where you say, if the qubit is up, I don't do anything. If the qubit is down, if the qubit is 0, I don't do anything. If it's 1, I do -1. So 0 becomes 0 and 1 becomes -1. That's the Z operation. The Y is a combination of X and Z. It's slightly more complicated. It's both not and this plus minus 1. There are other ones. There's an H, there's an S, and a T, but this is pretty much it. So the programming language of a quantum computer is really simple. There's just a very few building blocks. The building blocks are the C0, X, Y, Z, and perhaps the T, and that's pretty much it. And you can make the most complicated calculations just by stringing these building blocks together. So that's what we do. It's kind of fun that it's different. It means that if you're a computer scientist, or even if you're anything, and say, hey, I remember my father or my grandfather telling me when the first computers arrived in the 1970s, how exciting it was to have the first computer. But you say, I was born in 2010. I don't know. I missed it. I was born in 2000. I missed the dawn of the computer age. But you're here in the dawn of the quantum computer age. So you can learn how to program a quantum computer, and you'll know something which your father and your grandfather will not know. And you'll find jobs. At least in my country, this is a cool way for young people who study physics or computer scientists to find jobs. They learn how to program a quantum computer, and then they can be hired by companies who say, we want people with that expertise. We don't have them. Nobody here knows how to program a quantum computer. It's very much like it was in the 1980s. If in the early 1980s you knew how to program a computer, you found amazing jobs. The IT boom, it's gone now. I mean, now ChatGPT programs for us. They even tell us that coding jobs will disappear completely. They'll be completely taken over by AI. But quantum computer coding blocks will still be here. So that's good. Now, friends, I'm approaching the end of my hour. We'll have some little time for discussion and questions in a while. I want to close with 1 or 2 slides which sum up where we are. So I said that this is a century of quantum physics. So actually, everything I said today would be understandable to someone from 1925. Everything. Everything. Because it's all there. Entanglement, the plus and the 1, the superposition, all this stuff was discovered in the early 1920s, perhaps 1930. Entanglement is 100 years old. And it's not that people hadn't studied entanglement. In fact, it was studied quite extensively, but not by useful people. It was studied basically by philosophers of science. And you can even see books about this, which basically put entanglement in this weird corner of metaphysics, if you wish. This says the God effect, science's strangest phenomenon. The other says entangled minds, extrasensory experiences. So people thought that entanglement was some sort of, entanglement is this crazy thing that it's this magic bond which 2 people can have, even if they're instantly far apart, and by which they can somehow instantly affects what happens here and what happens at the other end of the universe. And something which Einstein said, by the way, which was crazy, couldn't exist. We know it exists, entanglement exists. This crazy action at a distance exists. And so philosophers of science are still struggling with that. But it was not something which you could make a living out. You couldn't find jobs studying entanglement, I can assure you that. And this has changed. In the 21st century, entanglement has become a source of technology. You can build companies, a company which uses entanglement to develop a business case. This could be the quantum internet, this could be quantum computer, it could be quantum sensors. There's a whole range of companies. Actually, what happens in my country is that young people who do a PhD in quantum science, then start a startup. They have their own startup. They said, I've learned something, I can make this device, I can make this, I can make that. I'm going to make a startup and I'll be the new Steve Jobs. Very much like it was in the 1980s when the first computers arrived and we had people like Bill Gates, like Steve Jobs, somehow say, this is cool, this is a revolution, we're going to do it. And so at least in my country, I have friends nearby, here in Leiden and Delft, who say, you know, my company will be the new Apple or the new ASML or whatever, because they've discovered entanglement as something which will change everything. We're not there yet. We're not there yet. So both quantum computer and the quantum internet are still a vision. And there are critical people out there. If you Google, you'll find critical people who say it will lead to nothing. It will just be some, you know, some academic stuff. People write papers. It will all just disappear. And it's quite possible. It's possible in science. This happens that people discover something which seems amazing and then turns out to actually not be that important. In fact, a recent discovery, which some of you may remember, is graphene. We had the discovery of graphene in 2005. People said, you know, this is the materials of the 21st century. Graphene will be the plastics of the 21st century. Europe, the European Union, had a special thing which was called a graphene flagship with €1 billion funding. You know, this would change everything. We're 20 years later and graphene is nowhere. It's still an interesting material. There's nothing wrong with it, but it's not this wonder material. So it can happen that scientists discover stuff. They're very excited about this. They write papers about it, but it doesn't really change the world. Or it could change the world, and we'll know. You guys are young. You'll know. Your children will know. Who knows? I may envision that. I'm kind of hopeful. So this is actually where I want to stop now, and so we'll have a little bit of time if anyone wants to ask me questions. And for that, I'm probably just going to stop the sharing so that I can see you. Anyway, just start, you know, you raise a hand and start talking if you want to.
Alper, we can have your question.
Okay, thanks. Professor, as you said earlier, I mean, you said quantum computers even cannot adapt to numbers. So based on your closure at the end, what's your vision? Is it in the negative sense or the positive sense?
No, so I'm very hopeful that we'll build large enough quantum computers that they can do something useful. B, discover an application which will be ideal for a quantum computer. This is not breaking codes. Breaking codes is just a silly application. It will not bring anything. But it could be, for example, in drug design. You know, there are these diseases, rare diseases, where somehow your body is not able to produce one particular protein. They're rare diseases. So the pharmaceutical industry doesn't really, they don't want to invest so much money and time to find this one antidote to your disease. But it could be that the quantum computer will just compute this. And you'll have personalized medicine where your own special deficiency will be able to be cured. And so we've been there before, you know. The generation of my mother, they were fearful of lots of diseases. We're no longer fearful of polio, for example. And we found vaccines, we found all kinds of antidotes. It could well be that lots of these ugly diseases where you cannot prepare a certain protein, ugly diseases that will just disappear. And our children will say, so can you imagine if we didn't have a quantum computer? So much suffering our parents had to go through. And this, of course, would be and it will be an obvious application because, of course, drug design is quantum physics. It's molecules which have to lock into each other. And if we can just compute it, And there are people who think about this in the way that we're now building aircraft. In the past, people would design an aircraft in a wind tunnel. Now an aircraft is designed on a computer. And so it may well be that quantum chemistry will move from the lab to a computer.
Yeah, Professor, thanks. And also, I think that the finance could really use up that space because as far as some of the calculations in finance is actually really similar to the physics equations themselves.
Absolutely.
Yeah,
But
maybe.
Albert, the problem a little bit is this. If I tell you drug design, I know for sure that quantum is going to help. If you tell me, let's say, machine learning, AI, it's all vague. We don't really know. So we do not know, as a matter of principle, whether a quantum computer is good for machine learning, is good for AI, is good for solving differential equations. We don't know. And this is actually this is an exciting topic of research. It's where what we're saying is find the killer application. Now, with computer, if somebody would have looked at a computer in 1950, 1960, would they have imagined the internet as the killer app?
No.
Nobody would have imagined that. And it may well be that this is what's going on at this moment, that we have these quantum computers, we're struggling to find application, we don't really know, and that someone will find the killer app. It might be quantum machine learning. I have colleagues in my university who think it is quantum machine learning. Who knows? It might be games. It might be that eventually we look back 20 years from now and we say, quantum computers, they're amazing for games. The games you can do in a quantum computer, they're mind-boggling. It's the only thing which came out of it, which is still good. Gaming industry is billion-dollar industry, but we don't know. That's the exciting time.
Yeah, right. Thanks for your feedback. The reason I just asked this question is because I cannot tell people it's the real future and it's coming out here. But the people who knows it, like really.
Any more questions? I see a couple of more hands.
I'm on the second order. I have a question actually about entanglement. So this summer I read an article. It was about in our brain there were quantum entanglement processes. So if we switch to quantum computers, can we have consciousness in our computers? This was my question.
Yeah. Okay. This is one of the. You mentioned another big unsolved problem. What is consciousness? Is it quantum? There are people out there who say that a classical, say, ChatGPT will never become conscious, but the moment you give it, you empower it with a quantum computer, it will become conscious. This is very much at the fringe of our knowledge. This is not something you can write in a scientific paper. I really don't know. And consciousness is one of these things we'll hopefully be able to resolve in this century. But at this moment, it's all, vague speculation or belief.
I also have a second one, if you don't mind. So for greater computing, we need either too much qubits or, the error correction. But we cannot have a great accuracy in our error correction if we use too much qubits. Isn't this a problem?
Yes. So this is actually something which is called fault tolerance. The problem is that if you add more redundancy to somehow correct for errors, you also produce more errors because these extra qubits can have errors themselves. And so if you would be unlucky, all the extra overheads you put in to somehow fight errors only brings you further from home. And this was the breakthrough of the Google team, who showed that actually they could introduce overhead which corrected more errors than it produced. And so if you go down that road, yes, you will be able at some point, if you're lucky, to have 100 fault-tolerant qubits. These are 100 qubits which live forever. Once you have 100 fault-tolerant qubits, a new era will have appeared. I mean, this is a mind-boggling thing which will be able to do things we've never dreamt of.
Right, thank you. So there's two more people after me, but they are carry on.
Okay. You said that the quantum computing can affect the game industry, right? Like, how can it affect? Can you give me more detail? Because
Oh,
I'm
there are
interested in
games
that
out there.
area.
There's quantum chess. There's all kinds of quantum games where you introduce entanglement, where you introduce teleportation, where you introduce superposition, where you introduce non-locality, which enriches the game. So you enrich a game by adding quantum rules. For example, imagine a chess game where a pawn can be at two places at the same time. It's quantum chess exists. Quantum chess exists. Quantum tic-tac-toe exists. There's already an industry developing quantum games. What we're doing in my university, we're using quantum games to teach people about quantum physics, which is a very modest way to do it, but it's a modest application. But that's one thing you could imagine doing, using quantum games to help people develop intuition from quantum physics. Young people, children, develop. This is the problem we are facing. Our world is a classical world. We do not understand quantum physics. We have to teach young kids to understand quantum. We're going to do this by means of games. That's what my university is trying to do. Please go ahead. There's Sean Tunaham. Go ahead.
I was going to say the exact thing. Like...
Oh, right. Hi. Thank you for the talk. It was really engaging. I'm pretty sure that this is a really stupid question, but it popped into my head when you kept sort of emphasizing the fact that quantum computers only implement reversible operations, but I sort of was thinking with my very vague computer science knowledge, we often rely on irreversible operations in classical computing, such as hash functions for security purposes. So with post-quantum cryptography, would that require a complete overhaul of these concepts such as hash functions, or is there a trick? Do we discard the ancillary qubits or something? So yeah, I was trying to.
I'm not sure that the hash function is an irreversible operation. It's more like a trapdoor function, right? It's something where I'm not sure that it's irreversible actually. I think actually no. From a computer science perspective, there's no big deal to have a complete logic and a universal computation which is fully reversible. Even this addition, I mean, you cannot add two numbers in the natural way. You would just need to have indeed an ancilla, some extra qubit which allows you to go back if you want to. So, but it's true that quantum codes which exist are fun. It's actually a branch of computer science which I'm not very well. I'm not expert in it all, but to use quantum codes to also develop more useful Hadamard codes, more useful nonlinear codes. And so this is something, a technical thing, which I would not be able to advise you any further.
Right,
Friends, I have to disappoint you at this moment. It's 1900, and as I said when I basically agreed to come here, yes, it's 1900 where I live, so it's 2100 where you are, and I have another appointment waiting for you. So I had 1 hour for you, and then that's gone. But I hope it's still kind of okay with you. I hope you kind of, somehow that was enjoyable. I basically enjoyed, even though I don't see your faces, I enjoyed being with you this evening. And I wish you all the best. Who knows, we'll see each other in real life at some moment.
Thank you for your attendance this night. It was a beautiful experience for myself and for all the people here. Thank you.
Very good. Take care, friends.
Take care, sir.
Goodbye.